All right, this is part 2 of a 2-part lesson on electric potential, i.e. voltage, and capacitors. All the images that you see in this video are attributed to OpenStax College Physics, published by openstax.org under the Creative Commons Attribution License. So capacitors. This picture, why don't we start by talking about the picture here in the front. This is a picture of what's going on inside your cells. The pinky area here is represents the membrane, a cell membrane, which is composed of phospholipids. It's a phospholipid bilayer. So these membranes are pretty good insulators. Ions can go across the membrane through ion channels that are embedded. These are proteins embedded in the channel, but the membrane itself is a pretty good insulator. And the cell uses a whole host of ion pumps and ion exchangers and energy stored in ATP to move ions across this cell membrane. So what happens is inside of your excitable cells, which are mainly your muscle cells and also your neurons, there's a significant separation of charge across the plasma membrane, across the cell membrane, and these membranes themselves act like storage devices for this charge, which are called capacitors. They have a separation of charge across the membrane, and the separation of charge establishes a voltage difference from inside to out. The voltage outside is higher than the voltage inside, and there's also stored energy by virtue of this separation of charge. So capacitors are, in general, these are devices that store electric charge. Let me start over. So capacitors are devices that store electric charge, and thus they store electric potential energy. And the plasma membrane, the phospholipid bilayer membrane of your cells, your excitable cells in your body, are capacitors. They separate charge and they store energy. Okay, well, capacitors, this is a picture of a, right here, of the most simple type of capacitor you could build. You have two conducting plates separated some distance d, and you connect one side, one of the plates, to the positive terminal in the battery, and the other to the negative terminal in the battery. So that means there's going to be a voltage difference from one of the plates to the other. The plates will charge up until the voltage difference from one plate to another equals the voltage of the battery, in which case current will stop flowing, and you'll have some fixed amount of voltage and energy stored on the capacitor. And we can characterize different capacitors in terms of a parameter called their capacitance. And capacitance is defined as the amount of charge that can be stored on a capacitor divided by how much voltage can be established between the two sides of a capacitor. So you can think of capacitance as charge per unit voltage. And the units of capacitance would be coulombs per volt. Here the C means coulombs, not C for capacitance. And this is equal to a unit called a farad, or abbreviated F for short. So it turns out a farad, 1 farad, is a tremendous amount of capacitance. Most capacitors are devices that have microfarads or nanofarads or even picofarads of capacitance. Most capacitors, most of the time, capacitors that you find in electric circuits are not of the parallel plate variety, like up here. Instead, they look like little barrels, something like that, with leads coming out the bottom, or they look like little ceramic discs. And so, but they all function in about the same way, and they consist of two conductors which are separated by some space, And usually that space is occupied by some insulator, which helps to enhance the capacitance of the capacitor. In essence, the insulator lowers the electric field for a given charge separation, allowing more charge to be stored at a given voltage, i.e. bigger capacitance. So capacitors store charge, and thus they also store energy. And there's a equation we can use to calculate how much energy a capacitor of a specific capacitance can store at a specific voltage. And it looks like this. The amount of, and this is a form of potential energy. So the potential energy that can be stored is equal to 1/2 times the capacitance times the voltage between the two sides of the capacitor squared. Where does this equation come from? Well, it's beyond the scope of this course. It involves some calculus, and so the derivation isn't important, but being able to use it is. One thing to point out here is since capacitance is Q divided by V, you can also write this as, you could plug Q divided by V in for C, and you get 1/2 Q times V, or you could plug in V equals Q over C to get a different form of this capacitance equation, or sorry, the energy stored in the capacitor. So in other words, this equation and this equation can be combined in a number of different ways to give you unique equations, different ways to find the potential energy stored on the capacitor. So in the next, over the next couple of units, we're going to start drawing schematics, diagrams of different electric circuits, and in those schematics, lines represent wires, and symbols that look like this, two parallel plates separated some distance, is the schematic symbol for a capacitor. Oop, off the page. And so this electric circuit here at the top is showing 3 capacitors connected to the same battery, and they're connected in series. And what series means is that if you go from the positive terminal to the negative terminal, follow a wire, make a circuit from the positive terminal to the negative terminal, you have to cross all 3 capacitors. There's no other way that you can go from positive to negative. They're in series with one another. So it turns out that, when capacitors are in series like this, effectively, it's like the battery is seeing one big capacitor that has an effective separation between the plates equal to the sum of the separations between the individual plates, and also it's seeing a capacitor plate that's or let me back up. So when the capacitors are connected in series, like they are up here, one way to think about it is the battery is seeing an effective capacitor that has a greater distance between the plates. In other words, it's almost like the distance between the plates adds together. Another way to think about this is when the capacitors are connected in series, they share the same voltage. They share the same battery, which means they have to split up the voltage among themselves, so no individual capacitor gets the entire voltage. So the net effect of this is that you can think about capacitors in series like this as one combined capacitor, where the capacitance of the combined capacitor, or I should say 1 over that total capacitance, equals the sum of 1 over C1 plus 1 over C2 plus 1 over C3. So the reciprocal of the total is equal to the sum of the reciprocals. And the net effect of this is that the combined capacitance, the effective capacitance of all 3 capacitors in series combined together, is always going to be less than any of the individual capacitances, C1, C2, or C3. In other words, CS is going to be less than C1, less than C2, and less than C3. It's smaller than any of them individually because of the way that they add together here mathematically. On the other hand, over here we have a circuit where 3 capacitors are connected in parallel. And in parallel, that means that you can trace a path from positive to negative around this circuit and do so in a way that doesn't require passing through the other capacitors. So it's almost like each of these capacitors is connected independently to the battery. You can trace a path from one plate of the capacitor back to the positive terminal and the other plate back to the negative terminal. For each of the capacitors, you can do that directly back to the battery. So what this means is that effectively each of the capacitors is seeing the entire voltage being supplied by the battery. Or turn that around, the battery is seeing an effective capacitor with a plate that's much bigger. So it's a capacitor that can store a lot more charge. So when you have capacitors connected in parallel like this, the combined capacitance, the effective capacitance of one capacitor that's equal to the sum of the capacitances of the individual capacitors is just the sum. So the combined capacitance equals C1 plus C2 plus C3. Okay, so that concludes this lesson, and we'll be talking about other circuit elements, including resistors and symbols for batteries in the next unit, and we'll start talking about currents and voltages and resistances all together so we can get an understanding of electric circuits.